The safety barriers around this junction are coated with a thin layer of zinc. If we look closely at the surface of the zinc, we see it's built up of many different patches. You can find this effect on a number of zinc-coated objects. The patches you see are crystals or grains of zinc. Here's a piece of a different metal. It's been machined along one edge. You can't see any grains in this surface. However, if we turn it over, it's quite a different story. This piece of metal has been broken in half. Along the broken edge, you can see some of the grains from which this material is made. All metals are made up of grains, although you'll rarely see them like this. In fact, with most metals, including this piece of aluminium, the grains aren't visible, not even on the surface. Here's a way of making them visible. First, we must give the aluminium a mirror-like finish. And there we are. Next, we treat the carefully prepared surface with a very powerful acid. Gloves are essential for this operation. As soon as the acids had time to react, the metal must be washed. It's then given a second treatment with another special chemical. We call this process etching. The particular chemicals used depend on the metal we're trying to etch. One final wash, and there are the grains. Grains of pure aluminium. They're all similar, both in size and in structure. They appear as different shades only because of the way they reflect the light. By etching, we can reveal the grain structure of any metal. Here's a different sample of aluminium. In this case, the grains are much larger and they vary in size. And here's a piece of copper. In this sample, the grains seem to get smaller as you get nearer the middle. Zinc, a sample whose grains are all shapes and sizes. But how do grains form? To find out, we've gone back to the stage when a metal is molten. In this furnace, the metal is aluminium. When the time is right, the furnace is tapped. The molten metal runs out along channels into molds to form huge slabs of aluminium. In turn, the solid slabs will be rolled into sheets. From time to time, a small sample of the molten aluminium is taken for analysis. The metal is poured and left to solidify. Now we can see what happens as the aluminium solidifies in a special film. At a number of points in the liquid metal, tiny crystals begin to form and grow. Each crystal grows outwards in all directions until it meets the surfaces of its neighboring crystals. In engineering terms, each fully grown crystal is called a grain. In this piece of solid aluminium, there's a very large number of grains. Now, once the aluminium's been cast into slabs, it's rolled into sheets. To get the metal down to this thickness, it's been rolled many times. It's now relatively cold, so as the metal is squashed between the rollers, it's being cold worked. Let's find out what effect the cold working has on the grain structure of the aluminium. Here we're etching a piece of the aluminium before cold working. At this stage, the grains are all approximately the same size and the same shape. Remember, they appear different shades only because of the way they reflect the light. Now we'll cold roll a similar piece of the same aluminium. In one pass, this machine will reduce the thickness by only a very small amount. So we'll reduce the gap between the rollers and put the metal through again. Right, let's see what that's done to the grain structure. The cold rolled piece of metal is the one at the top. Can you see the difference? We seem to have changed the shape of the grains. They've become elongated. We can get a better idea of what's happened in a diagram. First, we'll look at the grain structure of the metal before it's deformed. Here, the grains are normal. But as the metal is squashed between the rollers, you can see how the grains become elongated and distorted in the direction of rolling. The change in grain structure that results from cold working is accompanied by a change in the mechanical properties of the metal. Its hardness and tensile strength increases, while the ductility decreases. After cold working a metal, it's usually heated to a sufficiently high temperature. Let's see what effect heating has on the distorted grain structure. In the case of this particular metal, nothing happens until the temperature reaches about 350 degrees centigrade. Now, at the grain boundaries, new grains begin to form. These grow rapidly until a new, undistorted grain structure completely replaces the old, distorted one. We call this process recrystallization. Now let's see what effect this has had on the mechanical properties of the aluminium. Hardness, for example. Here we're measuring the resistance to indentation of a piece of cold-worked aluminium. How does this compare with the size of the dent produced in a piece of recrystallized aluminium? It's much deeper, so recrystallization has restored softness. And what about the tensile strength? First, the cold-worked aluminium. That needed a force of about 7 units to pull it apart. Now for a recrystallized piece. The force is going to be much less this time. The tensile strength has decreased. If we put the broken bits back together again, we find the recrystallized piece stretched the most, so we've also restored the ductility. However, the resulting properties depend on the temperature at which recrystallization is carried out. If the temperature becomes too high, some of the grains will grow at the expense of their neighbors. This can give rise to properties which are highly undesirable for most engineering applications. This is molten steel. When it cools, it will solidify and grains will be formed. Let's find out what the grain structure of a piece of plain carbon steel is like. We've given this piece of steel a mirror-like finish. Now we're etching it. The steel contains 0.4% carbon. So far, so good, but with the unaided eye, we can't see any grains. We'll have to take a small sample of the steel and view its surface through a microscope. Here it is, magnified nearly 250 times. Let's take a closer look at this in a diagram. In the case of steel, there are two different types of grain. We'll look at each in turn. The light grains, like this one, are made up of iron. Engineers call them ferrite. These give steel the property of ductility. The other grains, like this one, are made up in layers. The white layers are iron. The black layers are a chemical compound of iron and carbon, called iron carbide. Perlite is the name given to this type of grain. They give steel the properties of hardness and strength. This particular piece of steel is made up of roughly equal numbers of the two types of grain. So far, we've only looked at 0.4% carbon steel. However, steel can be produced with other carbon contents. What effect does this have on the grain structure? We'll start with 0.4% carbon, and let's add some more. Can you see what's happening? The number of perlite grains is increasing. Now there are no ferrite grains at all. The steel now contains 0.8% carbon. Under the microscope, a similar piece of steel looks like this. You can probably guess what will happen if we now reduce the amount of carbon in the steel. The number of perlite grains decreases, leaving a lot of ferrite grains. Now there's only about 0.1% carbon left. This is what a similar piece of carbon steel looks like under the microscope. Now we can change the mechanical properties of plain carbon steel by a carefully controlled sequence of heating and cooling by heat treatment. Let's find out what effect heat treatment has on the grain structure of the steel. The rings we're treating contain 0.8% carbon, so all the grains are of the same type, perlite. Nothing happens until the temperature reaches about 720 degrees centigrade. Now, at the grain boundaries, new grains begin to grow. These new grains are quite different to the original ones, and they grow until they completely take over the old structure. Here we're normalizing, so the components are taken out of the furnace and left to cool in air. Let's see what happens to the grain structure. As the temperature reaches about 720 degrees centigrade, the old type of grains begin to reappear. These grow until they meet their neighbors. This structure appears to be very similar to the one we started with. But if we compare the two, we find we've reduced the size of the grains and made them more uniform. We've also changed the properties of the steel. Here's a similar piece of untreated steel. Let's see how tough it is. Remember, toughness is its resistance to shock loading or impact. About 60 units. The broken surface reveals a very coarse grain structure. Now we'll test another piece of the same steel that's been heated to a high temperature and left to cool in air. About 100 units. It's much tougher. This time the broken surface reveals a much finer grain structure. In another form of heat treatment, plain carbon steel is heated to a high temperature and is then cooled rapidly or quenched in water. This treatment increases the hardness of the steel. Let's find out what it does to the grain structure. We're going to heat up a piece of 0.8% carbon steel to 750 degrees centigrade. Remember, with this particular amount of carbon, we have only one type of grain. Nothing happens until the temperature reaches about 720 degrees. Now, exactly the same thing happens here as it did in normalizing. New grains of a completely different structure grow out at the old grain boundaries. Right, now for the quench. As the temperature falls, in each new grain, a needle-like structure forms. This structure is very hard indeed. It's also brittle. We can relieve the brittleness by tempering. In this case, we're going to temper at about 500 degrees centigrade. Tempering modifies the structure of the needles. Inside each needle, small flakes of carbon begin to appear. Now the steel is much less brittle, but it's still harder than it was before heating and quenching. So far, we've only looked at the heat treatment of 0.8% carbon steel. What happens if we try to harden steel containing 0.1% carbon? Here, the grains are mainly iron. Again, nothing happens until the temperature reaches about 720 degrees centigrade. And once again, the new grains begin to form until they completely take over the old grain structure. In this case, we have to take the temperature up much higher to nearly 900 degrees centigrade. If we quench it now, there's insufficient carbon for the hard, needle-like structure to form. We've finished up exactly as we started.